Welcome to the second video in a series of 5 about graphing trigonometric functions. Here we're going to look at the graphs of sines and cosines. This video depends heavily on your understanding of a topic called graphing via transformations. You will not follow very much that happens in this video without that knowledge. If graphing via transformations, in other words, the shifting of graphs left, right, up, down, the horizontal and vertical compressions and stretches of graphs and reflections through axes is not something you've seen recently, you're going to want to start by spending an hour watching a 2-video series on my YouTube channel. Assuming that you're comfortable with graphing via transformations, let's proceed. Let's talk about this sine wave. We're going to create a graph here for the function y equals sine of x. Now, ordinarily when we graph, we think of a coordinate system like this. But when it comes to graphing trigonometric functions, we don't necessarily want to draw our graphs this big. As a matter of fact, if you look at the bottom of your screen, it's usually in this particular section where the most interesting features of the graph appear. And therefore, when we graph trigonometric functions, typically, we draw a graph that looks something like this to represent that one very important section of the graph. Now, it does vary from function to function, as we'll see as this video series goes on. But this is the typical way to start graphing a trigonometric function, to essentially just look at quadrants 1 and 4 in a reduced view. That being said, let's start plotting some points and see what happens. Remember back to the unit circle videos, or whatever you know about the unit circle. So I'm going to develop the graph of y equals sine x in a way that you as a student would not do. This is not a how-to moment in a video here, this is just a concept moment. As you see on your screen, I've pulled one of the 16 random facts about sine from our 16 favorite points on the unit circle. You may recall that the sine of 0 is 0. That indicates that my function should pass through the point 0, 0, so I'm going to put a point there. Here's another one of our favorite 16 facts from the unit circle. The sine of pi over 3 is radical 3 over 2. Now, if pi over 3 is an input to the sine function, and radical 3 over 2 is an output, that must mean, by definition, that my graph passes through or contains the point pi over 3, radical 3 over 2. Now, just to get an approximation of where this is, I reached for a calculator, worked each of these out as a decimal, and I got this. Where is that point? Well, it's right about here. Then I picked another random fact from the unit circle. You may recall that the sine of pi is 0. If at this point you're thinking, I don't remember the unit circle, you're going to need to go back and review that to have an understanding of how the sine function gets graphed. Back to the current moment, if pi as an input leads to 0 as an output, then the graph must pass through pi 0. So I put a point at approximately where pi 0 would be. Now, again, these are just arbitrary facts that I'm pulling from the unit circle to find somewhat arbitrary points on the graph of sine. This is not how you would go about graphing sine, but this is how I'm developing the idea so that you have a better understanding of the graph. We'll label that as pi instead of pi 0, just for visual clarity. And I could continue to do this with arbitrary points that I've selected from my favorite 16 on the unit circle. You may recall that the sine of 3 pi over 2 is negative 1. Therefore, the function must contain, or the graph must contain, 3 pi over 2, negative 1. I worked out 3 pi over 2 as a decimal just to get a sense of where this might be, and I plotted that point. Here's another fact from the unit circle, which led me to another point on my graph. And when I worked those out as a decimal, I got these, and plotted that point. I'll do one more of these. The sine of 2 pi is 0, and so the function must contain, or the graph must contain, 2 pi 0, which I've placed here, and we'll label 2 pi just to reduce clutter. Now, if you're thinking to yourself right now, so what do I do to graph trigonometric functions? Plot arbitrary points? No, I don't recommend that. But what I'm showing you is that when you do plot arbitrary points, you do get true points on the graph. Now, just from these dots alone, we don't have a real good sense of what the sine function would look like. Now, what have I done so far? I picked 6 of my random 16 favorite points on the unit circle, and I plotted them in relation to the function y equals sine of x. What if I were to plot all 16 points on the unit circle? All the ones that we like the most. Well, if I did that, I would get, hold that thought one second. I want to talk about this 1 for just a moment. We don't normally write that 1 there, because if you look at the x-axis, we're more interested in multiples of pi than we are whole numbers. I'm going to erase that. What I was saying a minute ago was, what if I were to plot all of the points on the unit circle that we care about, our 16 favorite? Then I would get 16 points. Actually 17, if you count the last one on the right. Nonetheless, this is the shape I would get. And you can kind of see what the graph of y equals sine of x is going to end up looking like. And I want to remind you that my favorite, quote, 16 points on the unit circle are definitely not the only points on the unit circle, just because they happen to be our favorites. So what if I were to plot literally every point on the unit circle? Well, you can't actually do that, but what you would get, the more points you plotted, is you would have the discovery that the sine graph looks like that. Now, if you're ever asked to graph the sine of x, you'll commit it to memory, and the picture in front of you now should just pop into your head. But I thought it was important that we develop it conceptually so that we know why the sine function looks the way that it does. Now, one other thing that's worth noting here is that this function is not only defined for x values between 0 and 2 pi, or what we think about as the traditional first rotation through the unit circle. This function is defined for all values of x, and the true sine graph looks a little bit more like this. In other words, the sine is what's called a cyclical function, meaning that it has intervals in which it repeats itself over and over. And what we're looking at in the middle to top of the screen is really just what we call one period of the sine function, which really extends the domain from negative infinity through positive infinity by continuous repetitions of this one period of the sine function. Now, traditionally, well, I should say that what we've really done here is graph the sine function only for x values between 0 and 2 pi. And traditionally, when we're asked to graph a trigonometric function, whether it's a sine, cosine, or any of the other 4, regardless of what it is, the expectation is that we're only going to draw one period of it, with the understanding that whatever we draw there continues to repeat itself infinitely in both directions. Now imagine we were to do the same thing with cosine. I won't take you through every single point here, but remember, there are 16 points on the unit circle that we care the most about. And if we were to take those 16 points, plug each of those radian values in for x, get corresponding y values, just as I showed you a minute ago for the sine function. These are the 16 points that would result from that exercise. If you need to pause for a minute, pick some points from the randomly from the unit circle, plug them in and see that these points are actually consistent with the values of the unit circle. That might not be a bad idea. But if you're willing to accept on faith for the moment that these are the 16 values that we would get, or the 16 points, if we were to do that, then it gives us a rough sense of what the cosine looks like in a graphic form in terms of it being a function. Now remember, our 16 favorite points on the unit circle aren't the only points on the unit circle. And if we were to do this with all points on the unit circle, then we would eventually discover that is what the graph of y equals cosine x looks like. Now, again, it's worth remembering, just as we saw for sine, that this is just one small piece of the cosine. The cosine is defined for all numbers from negative infinity to infinity. In other words, this graph goes on forever in both directions. And to get a slightly broader view of what we're seeing here, this is what the cosine graph looks like when you sort of zoom out. And this section that we graphed here with x values from 0 to 2 pi, again, is called one period of the cosine function. And when we graph trigonometric functions in general, again, we only graph one period of them, as you see in the middle upper portion of your screen, with the understanding that whatever it is we do graph when we graph one period of it repeats itself over and over infinitely in both directions. So what have we done so far? We've seen that the sine graph looks like this, and that the cosine graph looks like this. Now, at first glance, they may appear to be quite different. The sine graph appears to be sort of a mountain on the left and a valley on the right, if you'll accept the comparison, whereas the cosine graph appears to be one giant valley. Now, this is probably the wrong perspective to have, but it is one that we get sort of artificially by only looking at these graphs from x equals 0 to x equals 2 pi. If we broaden our view of these functions, here they both are in a more wide view, and what we see here is that they're exactly the same shape. In fact, one of them is just a shifted over version of the other. Here you can see which is which in the bigger picture. And so while we tend to only graph one period of a sine or a cosine when we're given them in a math class, and while they tend to look different, it's probably important to remember that ultimately they're exactly the same shape with a shift one way or the other. By the way, you'll notice at the title portion at the top of the screen that we're calling both of these a sine wave. Wouldn't one of them be a sine wave and one of them be a cosine wave? Well, since they're the exact same shape, for simplicity, we call them both sine waves. You'll also hear them referred to as sinusoids. There's no phrase cosinusoid, again, simply because they're exactly the same shape with a shift. So both of them are, in a more general sense, called sinusoids. So let's turn our attention to an actual example you might see in a math class. Here are the graphs that we derived for the sine and cosine functions. Those you should just commit to memory. Suppose we were asked to graph y equals 3 times the sine of 2x. The main thing to keep in mind when graphing trigonometric functions is that you don't have to think about them in any trigonometric way. For example, we're going to use the sine as the basis for this graph since we're graphing a sine. And this function here, for a moment, let's just pretend instead of this coming from trigonometry, that this were just some arbitrary function given to us, say f of x. And suppose further that this thing here that we were trying to graph was, rather than 3 times the sine of 2x, was just 3 times the function of 2x. If you look at what you have here, we could graph this based on the given function f of x, just using what we know about graphic transformations. In other words, when you're graphing a sine or cosine, you really don't need to think about it as a trigonometry problem. Just memorize the function and then ask yourself, what effect do the 3 and the 2 have in terms of a transformation of graphs? Now, what you may and hopefully recall from graphing of transformations is that when you multiply by a function by 3, you get a vertical stretch by a factor of 3. And when you multiply the argument of a function by 2, or the x by 2, you get a horizontal compression by a factor of 2. If this all sounds strange or unfamiliar to you, you've either forgotten or never learned your graphic transformations. And again, if that's the case, definitely want to go back and check out videos on graphing via transformations. But assuming this is all relatively familiar to you, then the only task at hand really is taking the graph of f of x at the bottom here, you may see it in gray, and stretching it vertically by a factor of 3 and compressing it horizontally by a factor of 3. And when we do both of those in conjunction with each other, we get the graph that you see here. Now notice we've done all this out of the context of trigonometry itself, just using graphing via transformations. Let's now put the trigonometry back and analyze this graph just a bit further. First, some vocabulary. This distance here, from the start to the end of the cycle, is called the period. So in this case, the graph has a period of pi. Further vocabulary, the distance from the center to the peak, or for that matter, from the center to the minimum, is called the amplitude. So here we have an amplitude of 3. Now, in addition to that vocabulary, one skill that you will probably be asked to display is the ability to take a graph of a trigonometric function, such as the one you see on the bottom of the screen, and to find a maximum, or a minimum, or an x-intercept, or all three of those. So let's now go about the business of finding those. First, we'll start with the x-intercept. There's a symmetry to sinusoid waves, so that point there is going to be the exact midpoint between 0 and pi on the x-axis. Notice where 0 and pi are on the x-axis. That arrow should be the midpoint. Now, for some people, it's obvious that the midpoint would be pi over 2. But if that's not obvious to you, you can use your pi algebra. If you haven't seen the pi algebra video, part 1 of this series, go check it out. Now, furthermore, let's go on to find this maximum point. Well, there's a further symmetry to sinusoids, so that maximum occurs exactly halfway between the two intercepts. So this new point that you see on the x-axis is the midpoint of 0 and pi over 2. Again, to some people, it's obvious that the midpoint of 0 and pi over 2 would be pi over 4. That's not obvious to you. Go back and check out the pi algebra video where more details about finding midpoints is given. But since that x-coordinate is pi over 4, then the actual maximum point itself must be pi over 4 comma 3, as you can see because of the tripling of the height of this function relative to sine x. Now let's go about the business of finding the minimum. Again, by symmetry, the minimum occurs at an x-coordinate that is the exact midpoint of pi over 2 and pi. Notice the x-axis, notice where pi over 2 and pi are, and we're looking for the midpoint of those. Again, if it's intuitive to you, then that would be 3 pi over 4, no problem. But if it's not intuitive, you simply have to use the midpoint rule, which, as a reminder from pi algebra video 1, you simply take pi over 2 and pi, add them up, and divide by 2. That will be the end result. And now that we know that that point has an x-coordinate of 3 pi over 4, the minimum itself is going to be at 3 pi over 4 comma negative 3. So now we've found all the pertinent points of one cycle of this function. All right, let's take a look at one more example. Let's suppose we're asked to graph y equals negative 2 times the cosine of x. Of course, we'd want to base this graph on the one that we memorize, y equals cosine x, as you can see here. So taking a look at the equation y equals -2 cosine x, it would benefit us to think of that -2 as a -1 times 2. The reason for this perspective is because it reminds us that by multiplying a function by -1, it will cause a reflection through the x-axis. And by multiplying a function by 2, it will give us a vertical stretch by a factor of 2. And so if we take the cosine graph that we see in front of us here, reflect it through the x-axis, and put it through a vertical stretch by a factor of 2, we'll get this graph. Just a little vocabulary here. This function has a period of 2 pi and an amplitude of 2. It's worth noting that the amplitude is not the overall height of the waveform. It's the distance from the middle of the waveform in a vertical sense to the top or bottom. And now that we've graphed y equals -2 cosine x, it's traditional to indicate the location of any maximum, minimum, or x-intercept. So let's do that now. The maximum would be at pi 2, as you can see from the graph. This minimum would be at 2 pi -2, as you can also see. This intercept here, because of the symmetry of sinusoids, would be at the midpoint between 0 and pi. Notice on the x-axis where 0 and pi are, this is going to be the midpoint. And if it's obvious to you that the midpoint there would be pi over 2, then great. If not, I refer you back to the pi algebra lesson where we learned how to find midpoints. And lastly, this x-intercept will be at the midpoint of pi and 2 pi, which turns out to be 3 pi over 2. And that completes the second video. Thanks for watching.